So I got an area of, what's that say, 360. So again, visually and also by this measurement, there should be plenty of room to doing a valve-in-valve TMVR in this particular case. So this is like a 45-minute procedure for us in the actual cath lab. So that's the easy one. The trickier ones, like I said, are with rings or with mitral annular calcification. So let me show you a MAC case real quick. But generally speaking, you know, if the valve is like 30, it's a 20, they put a 29 valve in, you're probably going to put a 26, maybe a 29 valve inside of it. So I've loaded a MAC case. This was one, you can obviously see there's 100% circumferential mitral annular calcification. This is not always the case. Actually, probably the majority of the time, what we'll see is we'll see someone with MAC, but maybe it's only encompassing 50% of the annulus or 60% of the annulus or something like that. There may not be MAC, you know, on this side, on the medial side, or on the lateral side, or whatnot. And that actually, the cases where there's circumferential MAC, it actually is somewhat easier because if you put a valve in here, it will hold in the middle. Well, hopefully we'll measure here in a second. It will hold in the middle of where it's the tightest, right? If you can imagine that there's no MAC on this edge, you try to put an off-label TAVR valve in there, what's going to happen is there's nothing that's going to hold the valve in place on the side that doesn't have MAC. And so those valves will embolize. So you do, in a way, want to have as much MAC there as possible if you're going to undertake one of these procedures. And so again, the starting off concept is still the same, and that is trying to define the annulus of the valve or of the valve that you are going to put a valve inside of. And so for these MAC cases, you don't have a current valve in there as your landing zone. What you have to figure out is, based on the distribution of the MAC, where is it going to be the tightest? Like if you were to take a valve and drop it, if you're looking down at the mitral valve and you drop it in there, where's it going to get stuck? And so what I'm essentially doing here is scrolling up and down to see where it looks the tightest, where there is the best distribution of calcium to actually hold the valve in place. And my guess is, and this is why these cases are tough, because there's not exact science in this, maybe around here, right? And so what I'm going to do is I'm going to make two measurements, one of the commissure, which is this dimension here. There's some blooming artifact, obviously, but roughly 31-ish, 32 millimeters. And then that's your intercommissural distance. And then I'm going to make another measurement of the AP dimension. You know, so roughly here to there, right? If you didn't have any anterior MAC, like this would go all the way up to here, right? And the valve would just kind of tip over and fall through into the LVOT. But the one that matters the most is this intercommissural distance, which is usually the widest. And so this is measuring, click out of this. This is measuring 31.8 millimeters. So the largest SAPIEN TAVR valve is 29 millimeters. And if you pump it up, you can maybe get it to 30 millimeters. And this is another one of the challenges with these valve and MAC cases. If I put a valve in there, it ain't going to fit perfectly, right? It's going to be really tight in the AP plane, and it's going to be not big enough in the septal to lateral plane. In our experience, a lot of these do tend to circularize a little bit, but this is a case where I would be concerned still. Let me just make sure this is a 29 valve in here. Yeah, it's a 29 valve in there. This is a case that I would still be concerned that you're going to have leak on this side, right? Or if this valve gets deployed on this side, you're going to have leak on that side. So you would have to be prepared to do an ad hoc paravalvular leak closure at the same time, which is going to add another hour to the procedure. So let's just say that the valve in the short axis plane will sit somewhere like that. Then you have to adjust your long axis plane to make sure that you are not either too deep in the ventricle or too shallow in the ventricle. If you are too deep in the ventricle, what you're going to risk is what we just talked about in the last case, obstruction of your LVOT, right? Like this is completely blocking off your LVOT. If you're too shallow, what's going to happen is you see this pink line right here? That's what's called the skirt of the valve. This is otherwise a bunch of open cells in these stent frames. If you put the valve up here where the pink line is not touching your MAC, you're going to have leak through these open cells and you're going to have paravalvular leak. So you have to put this thing basically somewhere where the MAC is touching the pink line, but you're not closing off the LVOT. And again, this is not exact science, right? Like I could put this thing literally, if I move it 1 millimeter one way or another, it's going to change some of our measurements for LVOT, which is what we're going to do next. And the other thing is that in the lab, you don't have this type of finite control. Like the valve is ultimately going to sit where the proceduralists are able to deploy it. And so this is not a perfect prediction of LVOT risk. But I will say that certainly if the valve is touching the septum, you're probably going to be at high risk. So this one, same thing. I drew out the LVOT already before, and then I basically go ahead and I measure where it looks the tightest. And I already made a measurement from before. So I'll just click on that to show you. And look at this area. Look at the difference here. 87 millimeters squared, right? And 200 is a safe cutoff. 180 is like a bare minimum. So this is a case where visually it looks like it's going to be tight. And then more objectively, it for sure is going to be tight.